You know that little knob in your car, the one you twist to brighten or dim your dashboard lights? It seems, well, pretty simple, right? But believe it or not, behind that simple twist, there's some really clever engineering going on. Today, we're going to pull back the curtain and see the surprisingly simple principle that makes the whole thing tick.
I mean, really think about it. How does that one little physical action have such a precise, immediate effect on a light? It's not magic, I promise. It's actually a fantastic, real-world application of a basic electrical concept, and we are going to totally demystify it right now.
So here's our game plan. First, we'll tackle the mystery itself. Then we'll look at the electronic blueprint, kind of like a recipe. We'll see how it's actually built, zoom in on that all-important control knob, and then, this is the fun part, we'll look at the data to uncover the simple rule that makes it all work. All right, let's dive right in. The mystery of the dimmer knob. How can a simple twist translate into such a smooth change in light? The answer, it turns out, is hiding in one of the most fundamental ideas in all of electronics. And here it is. This is the absolute key to everything. The more electrical current you push through a lamp, the brighter it gets. The less current, the dimmer it gets. It's really that simple. So that knob in your car isn't really controlling light at all. It's controlling electrical current. So the real question is, how does it do that? Well, to figure that out, we need to think like an engineer. And before an engineer builds anything, they draw a map for the electricity. It's called a schematic diagram, and it's basically the circuit's recipe. And here it is, the blueprint for our dimmer circuit. I know, it might look a little intimidating with all those lines and symbols, but don't worry. Just think of it as a roadmap, showing all the parts and the exact path the electricity is supposed to follow. Let's break down what these little symbols actually are. Okay, so what are we looking at? We've got our 12-volt power source, the car battery. There's a fuse for safety, super important. A simple switch to turn the whole thing on and off. The lamp, of course. And then there's this guy, the squiggly line with an arrow. That's the potentiometer. That, right there, is our dimmer knob. He's the star of the show. Now, in the real world, you don't just go from a drawing to a final car part. No way. You've got to build a prototype first to make sure it all works. And for that, engineers have this amazing tool that lets them build and rebuild circuits without any permanent connections. And this is what it looks like when you take that blueprint and bring it to life. Here you can see all those components from our schematic, the switch, the knob, the lamp, all wired up on this white plastic board. That board is called a breadboard. So what exactly is a breadboard? Honestly, the best way to think about it is like a Lego board, but for electronics. You just stick the components and wires into the little holes, and they connect up. It's awesome because you can build something, test it, and if it doesn't work, just pull the parts out and try again. No soldering needed. Okay, let's zoom in on our hero component again, the potentiometer. That's the thing we're actually physically turning. It's the heart and soul of this dimmer circuit. So what is it actually doing when we twist it? A potentiometer is just a fancy name for a variable resistor. And here's the perfect analogy for it. Imagine electricity is water flowing through a pipe. A resistor is like a section of that pipe that's a little bit narrower, slowing the water down. A variable resistor, our potentiometer, is like a faucet. You turn the knob, and you're literally opening or closing a valve, controlling just how much water, or in our case, electrical current, is allowed to flow through. So we've got this awesome faucet analogy. Turning the knob changes the flow, but that's just a theory, right? How do we prove it? I mean, you can't see electricity. That's where a tool called a multimeter comes in. It's like a pair of magic glasses that lets us see the invisible electrical forces at work in our circuit. So let's ask the big question. How does adjusting our electrical faucet actually change the flow? Let's get our multimeter out and take some real measurements. Check this out. We took 2 measurements. In the first one, let's call it measurement A, our multimeter says there's 40 milliamps of current flowing. Then we turn the knob a bit, and in measurement B, the meter reads 60 milliamps. So yeah, we've definitely changed the flow. Okay, so let's tie this back to what we learned at the very beginning. For which measurement is the lamp brighter? Well, we go more current means more brightness. So it's obvious. The lamp is way brighter in measurement B with 60 milliamps than it is in A. Awesome. We've just proven the first half of our theory. But why did the current change? What did the knob do? And this, my friends, is where we connect all the dots. We're about to uncover the simple, elegant rule that makes this entire dimmer circuit work. It all comes down to one thing: resistance. Now we use our multimeter to measure resistance, which is basically how much the circuit is fighting against the flow of electricity. It's measured in ohms. Look at this. In position A, where the light was dim and the current was low, the resistance was super high, 510 ohms. But in position B, where the light was bright and the current was high, the resistance was way lower, only 260 ohms. Do you see it? This is the final piece of the puzzle.
This table just lays it out perfectly. When we turn the knob to create high resistance, it's like we're cranking the faucet almost shut. We get only a trickle of current and the lamp is dim. But when we turn the knob the other way and create low resistance, we're opening that faucet wide open. A flood of current gets through and the lamp gets super bright. It's a beautiful, simple inverse relationship.
And that's the big takeaway. The whole secret is this: to control a light's brightness, all you have to do is control the resistance in its circuit. We're not really dimming a light, we're just making it harder or easier for electricity to do its job. The dimming is just the result. It's that cool? So the next time you get in your car and give that little knob a twist, you'll know exactly what's going on beneath the surface. You're not just dimming a light, you're playing the role of an electrical faucet. Which makes you wonder, right? What other things in your life, like the volume knob on an old stereo or the speed control on a ceiling fan, might be using this exact same beautifully simple principle? Something to think about. Thanks for tuning in.